Okay, good afternoon, everyone. Let's get started. So today I just have one more slide to follow up on what we were talking about last time, and then we're going to launch into a new topic that will take us through the rest of this unit. So last time we talked about how it was useful to split your full data set into training and test pieces or folds. And then you design your beta parameters on the training data, that's your model parameters. And then to do other things like model order selection, you use the test data. For example, you measure RSS on the test data for different model order Ds, and then you choose the one that works best. And there was a fancier approach we used, the one standard error rule. But I wanted to bring up that sometimes there's a third fold, and usually people talk about it in terms of training, test, and validation. And so that third fold is something that you use once you've done your model fitting as well as your hyperparameter selection, and now you've come up with your final model that you think is good to use in the real world. You still often might want to do one more stage of testing on data that you have not used for either training or model order selection. And so we will call that validation data. So that you'll do one more validation of your model on some data that haven't seen before. So that's just the main point here. So sometimes you have training, test, and validation. And one place you'll see this validation data is there's a lot of machine learning contests where they will put up data for users to use, and the users competing, the contestants, will take that data and they'll somehow split it into training and test. But then the people running the competition will be holding privately another set of data, another fold that's the validation data, because they never share it with the contestants, obviously the contestants cannot use it. They can't cheat with it. And so but then the competition is scored based on that final privately held data. Okay, so that's one place this will show up. And so when we do our final project, we will do an internal Kaggle competition, and it will work like this. There will be a part of the data that only I and the TAs will see, and that will be the data that you're finally scored on. And then the final comment regarding this is that the names test and validation are not consistently used in the literature. So sometimes when people talk about test, they're using it to refer to the stuff you use to tune your model hyperparameters, and validation, the final, holdout that you use for performance. But then sometimes they switch them. Sometimes they say that you use your validation data for model order selection and your test data for the last step. And there's nothing consistent. So you just have to be aware that you have to maybe read a little closer at the context to see when someone says validation or test, what are they really meaning? Those two terms are used interchangeably, even though they might mean different things. Okay, so in this unit, we have only considered training and test. We have not held out any special data that we use at the end after we fit our parameters in our model order. But I just wanted to bring this up because it is something you'll see in practice. Okay, any questions on this? Okay, great. So now we've seen some practical stuff, and we're going to generalize things a little bit more and look at the theory behind it, just in a very basic sense. The simplest kind of theory one can do for machine learning, we're going to do that. So sort of as a high-level overview, we have studied until now degree D polynomial regression, and we saw that if you choose D too small, we get underfitting. If you choose D too large, you get overfitting. And we said we can optimize D by minimizing the test sample RSS. through cross-validation. And so we talked about different ways of doing that. But this is really just a special case of what you see in practice, because polynomial regression is just one very special case. So in practice, you see always, you construct a model to do your machine learning, and you have a lot of flexibility in how you construct that model, how simple or complex it is. So basically, we still have the same things happening. If you have a model that's too simple, that causes underfitting. If the model is too complex, that causes overfitting. And we can manage our complexity by minimizing some appropriate metric, which might be RSS or it might not, through cross-validation. So for example, soon we'll start studying classification. When we do that, RSS is not going to be the metric we care about, but we can still do model order selection, we can still do cross-validation, all that will be the same. So the metric might change, the details of the model might change, but what's in common is that too simple is underfitting, too complex is overfitting, and you somehow want to optimize the complexity. Okay. Any questions so far on that? Okay. So what we're going to study next is we're going to look at sort of a theoretical perspective of regression. And we are going to look at something called mean squared error, which we can think of as the statistical version of normalized RSS. And by statistical version, we're going to have to get into some details involving expectation, probability, and so on. And what we'll see at the end of this, we're going to do an analysis of this mean squared error quantity, and it's going to lead to one of the most important concepts of the semester, which is the bias variance equation. And we'll see, in studying that equation, we'll see a direct trade-off between two terms, bias and variance, that get weighted in different ways as your model goes from simple to complex. So this we'll finally get a bit of a clearer viewpoint on, for example, why do we want more training data? How does that help us in terms of, because we know intuitively more training data should be better, right? We're gonna prove that it is, and exactly how it's better through this analysis. All right. So any questions on anything? Okay, so that's the introduction. So what we have to do first is we have to just do a little bit of review. And this is all stuff that is a prerequisite, so I'm assuming you guys have seen this before. I cannot teach you all this from scratch in the matter of a few minutes. It's impossible. So my point here is to kind of just remind you of some things that you've hopefully learned in the past and say these are the important ones for us. You don't have to know everything about probability and random variables, just a few key things. So I'll point out the important things for us. I'll establish some notation, and then these will be the tools that we will use for the rest of this unit, and you'll need them for the homework and so on. Okay, so we're going to now talk for the first time about this concept of randomness. So, why do we use randomness? We haven't used randomness at all so far in the course. We have dealt with, data sets that are just a list of numbers. That's all they are. There's nothing random about them. It's just a list of numbers. If we want to model randomness, we can do this, but we have to do it with a particular set of mathematics. It involves random variables. So what is a random variable? I would say from an intuitive perspective, a random variable is like a bag of marbles. If I have a bag of marbles, and each marble has a number on it, let's say I pull out a marble from the bag, like sometimes when I pull it out, it says 0. Sometimes when I pull it out, it might say 2, and so on, right? Every time I pull out a marble, it could be different. It could be the same as last time, or it could be different. And now if you look in aggregate of what happens in general when you pull out marbles from this bag, maybe for a particular bag of marbles, you notice all the marbles are either 0 or 1. And the chance that I draw 1 is twice the chance that I draw 2. So that would be an example of a random variable. a random variable that takes on the values 0 or 1, and the probability it takes on 1 is twice than the probability it takes on 0, but that's all that can happen, right? Or you could have a bag of marbles where every time you pull one out, it's a real number. You might notice that the real numbers are always positive, so that's something about the statistics of that bag or that random variable. So just in terms of random variables, think of them as bag of marbles if you want. But basically, there's two types of random variables. There's discrete random variables and continuous ones. So discrete ones are the ones like the 0, 1 random variable. The realm of possibilities for a discrete random variable is countable. It could be infinite, like it could be any integer. There's still an infinite number of integers, but it's countable. They're discrete in that sense. On the other hand, continuous random variables, they're uncountable. They're something like the real numbers or the real numbers between 0 and 1. There's still an uncountable number of them in that interval. So that's the difference between discrete and continuous random variables. So let's get some notation here. So just in some of these intro slides here, I'm going to be using capital letters for random variables because that's very typical. You'll see that in textbooks. And pretty soon we will depart from that because that really constrains our notation for this course. But just at the beginning, I'm going to focus on I'm going to use capital letters for random variables. So if I have a discrete random variable, capital A, then it means that it can take on values, like I said, from a countable set. And in this case, I'm going to label the possibilities like A sup 1, A sup 2, A sup k, and so on. So in this particular case, there's a total of k possible things that can happen, k different ways this random variable can manifest. The way that you describe how often those k things happen is through the probability mass function, which is just a vector of the respective probabilities. So for example, the probability that this random variable manifests as A1 is PA1. That's a number that has to live between 0 and 1, right? Probability can't be negative. Probability can't be greater than 1. When you look at all these things together, the probability that any one of them happens is 1. So when you sum up these probabilities here in this vector, they must sum up to 1. Okay, so that's one of the properties of this probability mass function. It's a vector where the elements sum to 1, and all the elements individually live between 0 and 1. Okay, so this is the definition. Probability, or PAK, is a probability that the random variable A takes on the value A sup k. Is everybody good with this? Okay.
Professor.
Yes.
The maximum value of probability mass function is 1.
The probability mass function is a vector.
Okay.
It's a vector of values. Each value is between 0 and 1.
The summation of those elements
Must be 1.
Will be 1.
Yeah, no matter what, it has to sum to 1. Okay, continuous random variable. Again, we'll call it A. It's a little bit more complicated to deal with. There's two ways that we tend to summarize it. There's the cumulative distribution function, or CDF. This is a function that says, so if we say the CDF of the random variable A evaluated at the number little a is the probability that this random variable is less than or equal to that number little a. Okay, so that's what the CDF means. More often we deal with its derivative. The derivative of that with respect to A, that's the PDF. That's a density function. Similar in spirit to a histogram, kind of, but histogram is something we compute from measured data, whereas a PDF is a kind of a theoretical quantity that describes a random variable. So a few properties now of this PDF. Or this is, I guess, one way we can see the relationship between the CDF here on the left and the PDF here on the right. If you integrate from minus infinity up to the value a of that PDF, that's how you get the CDF. That's why it's cumulative. And from the fundamental theorem of calculus, you can see that if you differentiate this with respect to a, you'll get back that PDF. Okay, so the main properties here is that that function must be non-negative, and it must integrate to 1. So it's similar in spirit to the PMF in non-negativity, but we have to replace the sum with an integral. Okay. The values within the density, they can be arbitrarily large. They're not capped at any number like 1. Okay. If you want a nice summary of all this that's sort of similar to that linear algebra handout that was pretty concise, just a few pages, but covers all these topics, I wrote one for you, and it is here, down here. You can find it on the GitHub page, or you can click on this link and it will take you to that GitHub page. But basically, I just try to go through in prose and describe all this step by step. So that could be a good reference if you don't have a probability book that you used back when you learned it. Okay, any questions on continuous random variables? Okay. So there's a lot of things you can do with these PDFs and CDFs, but we're going to focus on expectation. Expectation is one of the simplest, and it's just the statistical version of the mean. We learned the sample mean before. The sample mean is something you can apply to a set of data that someone gives you, a list of numbers. The statistical mean is something you can only apply to random variables. But it has very similar meaning. It's just the average value of that random variable. So if I have this bag of marbles and you say what's the number on average of the marble that comes out, that's the mean. That's the expectation. Okay, so how do we define it? So the expectation of, and so the definitions here I'm going to write using functions, any function. It just helps to flesh it out a little bit. So if you have a random variable and any function, that function could be, for example, squaring it or taking the cosine or anything, whatever you want. The expectation of the function of a is an integral over the real line of f, and now I'm going to use a dummy variable little a for this integral, and I'm going to have the PDF. Oh, sorry, this one is down here, the continuous one. Let me start with that since I've started already. So we have P of A dA. Okay, so so this is how we basically connect the density to this statistical expectation. I'm not going to dwell on this in this course, but if you ever have some question about expectation, you're like, why does expectation work in this way? You can always prove it using this. That's like your first principles. So whenever you have a question like, why is it, what's going on here, you can come back and you can use it in this form, and just using basic calculus, you can answer a lot of questions for yourselves. Okay, now, the case where we have a discrete random variable, instead of an integral, we have a sum over all the possibilities. And now we're going to have function of a sup k times the probability mass function PA, comma k. Okay. So it's like a weighted sum in this case. You have all the different possibilities the function can manifest as, and now you're just weighting them by the probabilities of that happening. So it's just a weighted sum. And then this, you could say, is just kind of like taking that sum all the way to an integral, in some sense. It's like from the Riemann sum perspective, you can think about it like that. If there's an infinite number of possible things that can happen, that sum turns into an integral. but otherwise you get essentially the same form. Okay, so how are you guys doing with this? Is this jogging any memories from some terrible class you took sometime in the past? Okay, so like I said, we're not going to dwell on a lot of this stuff, but we will need to use expectations very frequently, and there's really only a couple things you need to know about them that will cover all the bases. Basically, two properties, linearity and independence. So first, we'll start with the linearity property. So here, I have C and D are just deterministic constants. These are not random variables, they're just some fixed numbers. Here is some function f, it could be any function, and here's my random variable a. Okay, so if I take the expectation of C plus D times the function of a, what do you think happens? So let me get out my list here. So is Dion Chen here? Yeah, so what happens here, Dion? What do you think we get from the, just maybe from an intuitive perspective, you can answer it without even getting lost in the math.
Actually, I have no idea about that.
No idea, okay. So what's gonna happen is you're just gonna get C plus D times the expected value of FA. Okay, so in other words, expectation is a linear function. So by linear function, it means if you take the expected value of a sum of two things, that's the same as the sum of the expectation applied to both. Okay, so that's what allowed us to say that this is the expected value of C plus the expected value of the second term. Now for the second term, another way that linearity works is expected value of a scaled version of FA is the same thing as the scaled version of the expectation of FA. So we can pull the D through the expectation to get into this form. Okay, so this is the linearity property, and this is going to be something that you're going to use over and over and over in derivations, homeworks, and all that. Question?
Is there a significant, are you drawing the F's as all lowercase, or it looks like there might be a couple places you're putting a capital F, is that something?
They're all lowercase.
Okay.
Sorry for my bad handwriting. It's all the lowercase f.
I know, I'm just used to.
Yeah.
Cool.
Okay. All right. Any questions about the linearity property?
Yeah, Professor, why we didn't use E with C? C plus DE. In the linearity property, we used only expected value for function A.
Okay, yeah. So good question. So I think the question is, what happened to this? So by the first step of linearity, I'd have expected value of C. So in this case, C is not random. It's a deterministic number, meaning non-random. So if you say, what's the average value of, let's say, the number 1? Well, it doesn't fluctuate. It's just 1, right? So for any fixed number C, the average value of C is just C. It's not random. Okay, so that's what happened. That's why we took out the expectation on C. Okay. All right, any other questions on linearity property? Okay, now we have a second property which we can apply if and only if the two random variables A and B are independent, statistically independent. So here we have on the left expected value of a product of some function of A and some function of B. So in the general case, we cannot break this down anymore. We're stuck here. But if you tell me A and B are statistically independent, then you can break it into, let's take a guess. So is Kevin Donnelly here? Kevin? No. Okay, what about Jijuan H-E? Yeah, so what do we get here if A and B are independent? Exactly. We get the expected value of the first one times the expected value of the second one. Okay, So often in a derivation, that will lead to a great simplification because then you can attack each of these individually, and that is a lot simpler than trying to figure out what's happening with this crazy combination of all these random variables together. Okay, so this happens if and only if they are independent. If they're not independent, you can't use this property. What does it mean to be independent? So, when we talk about two random variables that might be related, we have a joint probability density function. It behaves like a PDF, except there's just two numbers instead of one. And when those random variables A and B are independent, that means you can factor it into one part that depends only on A, the other part that depends only on B. Okay. So if you want to prove this, essentially you take this and you combine it with this, and in a few lines, you got the proof. Similarly, if you want to prove this, you basically take this and you plug this stuff in here, and that will come out. So it's all there. If you have a question or anything, in most cases, it's pretty easy to figure it out, even on your own. Okay, any question on the second one? Okay, so expectation is something that we very often do. Another thing that we'll sometimes do is look at the variance of a random variable. So in spirit, this is like our sample variance, but it's not with a list of numbers, it's with this random variable. So does anybody have a guess? Let me see, is Po-Yin Huang here? Any idea how we define the variance? So in spirit, it's the same as what we did with the sample variance. Okay. Uh-huh. So the first thing we have to do for variance, even sample variance, is we had to subtract the mean from the variable, right? So to do that, I'm going to take A, and I'm going to subtract the mean of A. So now I have something where I subtracted the mean, and now the next step is square it, exactly. Square it. And now, yeah, so the difference is before we had an averaging sum, now, which is like just a deterministic kind of average. Now we have a statistical average, which is the expectation. Okay, so this is the variance. So we have one expectation on the inside, and we have another one on the outside, and this squaring operation. Okay, and again, this expectation and this expectation are defined in the same way up here. So if you want to prove things about this, it's just a matter of calculus. Just put things in there, move things around, you can prove stuff. Okay, great. Any questions about variance? All right. Oh, question? So this is, yes, so there's other ways we can write it. Let me write it in a slightly different way. Let me first move things around so I have a little bit more room. Yes, it's a great question. So another way to write this, which is essentially we did this with the sample variance, we proved this, is you can look at the expected value of A, the quantity A squared, and then you can subtract the mean squared. Right? We did this before. Instead of the expectation, we had an averaging sum. Now it's exactly the same as before, and the proof is also more or less the same. So just to clarify, when I write this, and the 2 is outside of the curly braces, you apply the expectation first, and then later you take the square. If we want to take the square first, we put the square inside the curly braces. Yeah, great question. Yes.
For the random variable A, should we expect that we know what are the sample numbers are, or we know that what are all the possible numbers?
So the random variable is like this big bag of marbles, right? So in some sense, the bag of marbles is a completely separate idea from the specific marbles you can take out of it, right? So when we talk about the bag of marbles, we can know things about the bag as a whole. We can know, like, what is the average value? What is the minimum value? What's the maximum value? And so on. Those are the sort of things we know about random variables. But the way that we really fully describe a continuous random variable would be the PDF, and the way we fully describe a discrete random variable is the PMF. So that's the way we're going to describe it fully. And from the PMF and PDF, you can get any simpler statistic. Like here is how we go from the PDF to the mean, which is a simple statistic. It doesn't tell us everything. Or, using that PDF, you can go to the mean and then the variance. So you can see how you can get all the simpler things from that one quantity, the PDF, that tells you everything about that random variable or that bag of marbles. Okay, great.
Is that expression is same for discrete random variable and continuous random
Yes, yes. So all this stuff here holds for both discrete and continuous. Yeah, it's just the details of how you do the expectation, they change. Okay, good. Any other questions? Okay, so now moving on to a bit of a trickier topic and I think a lot more interesting, is conditional expectation. And this is really where we get into machine learning, because in machine learning, you're trying to predict, right? You're trying to say, you have targets and you have features and you want to know the relationship between them. So you have, maybe you're given the features and now you want to know the target. So that's the spirit of conditional expectation. Okay, so let's take a look. Conditional expectation has a form like this. The expected value of some function of A, and then there's this vertical bar, and then this is the thing that you know. This is what you're given. So you would say, the way you would read this, you'd say the expected value of FA given that the random variable B takes on the specific value little b. So you can sometimes call that an event, the event that random variable B takes on the specific value little b. Let me give you a flavor of this. So maybe random variable A is, maybe it's 0 or 1, which means the sidewalk is wet. Sidewalk is wet when it's a 1, sidewalk is not wet when it's a 0. And let's say that B, which will also be in 0 and 1, is that it's cloudy. Cloudy if 1, sunny, not cloudy 0. So on the previous page, we talked about things like expected value of A, which in this case would be what's the probability that the sidewalk is wet, right? How often is the sidewalk wet? So in Columbus, I don't know, maybe the sidewalk is wet 10% of the time, something like that. Now, if I tell you, if I ask a question, how often is the sidewalk wet given that it's cloudy outside? Now things have changed, right? If it's cloudy outside, it's more likely that the sidewalk is wet. So you have these two random variables. One is cloudy or not cloudy. You can think of that as random because we don't really know what it's going to be, let's say on any given day in the future. And then we have sidewalk being wet or not. And these things are related statistically, right? They're coupled. So we can talk about things like that. What's the what's the expectation that the sidewalk is wet given that it's cloudy or not cloudy? So that's the flavor of conditional expectation. The way that we define this in terms of an integral, which is again the way you would prove a bunch of stuff, is similar to before. You have f of a in the integral, and now the thing that changes is that instead of the PDF, you have a conditional PDF. PDF of a given b oh, I'm sorry, I actually need to, this should be a little a here, little a, and then I have my dummy variable a given b, dA. Okay, so this is, so a is just the dummy variable of integration. You know, I could really use anything, but I'm just going to call it little a because it's representing the value of the random variable capital A. And now I have this conditional density. So this thing, you could say that this thing is the density, the PDF of A, given that you have this specific event that the random variable B is little b. Or maybe it's not a, you know, we could also do the version of this with the sum instead of the integral. But that's essentially how this is built. So it's very much the same as expectation. The only difference is you put in the conditional PDF rather than the non-conditional PDF. Okay, and with this, you can prove just about anything you want to prove about conditional expectation. So before I move on, is the kind of idea of conditional expectation making sense? Average value of one thing, given that some other related statistical quantity is fixed. Yes.
Could you substitute it for the conditional PDF using Bayes' theorem?
We're going to talk about Bayes' theorem later. There's all sorts of things we can prove using Bayes' theorem, but for now, I'm not going to get into it if that's okay. Yeah, just kind of starting with the definition. But yeah, I mean, you'll find all this stuff in this Bayes' theorem and everything in this thing that I typed up. Okay, so so the way I described it so far is that this second random variable is taking on a very specific thing, like it's cloudy. You know, what's the probability that the sidewalk is wet given that it's cloudy? So you know it's cloudy. But the way that you'll often see this is with this specific equals b left off. So you might just have expected value of FA given b, where b is now not the specific little b, which is deterministic, it's actually the random b itself. So it's just like this concept, like the original one, but the little b is random. So that's the way I would describe it. And this is itself now going to be a random variable. So usually when we take the expectation of something, it's no longer random, right? All the randomness has been squashed out because you're looking at the average value. But when you deal with this conditional expectation, it's kind of like the mean of this changes for every value that b can take on. And since b is random, it can take on many values, which means that this overall thing becomes random. Okay, so that's conditional expectation. Now again, there's really just a few basic quantities that we'll use over and over again. So I'll go through those next if there's no questions. Okay, so the first useful property is going to go like this, and it's a little bit intuitive. So let's say you have this big ugly thing, which is some function of a times some function of b, and you want to know what is this on average, given that someone basically tells you what a is. So what do you think happens here? How can we simplify this? Let me ask, is Eric Schwegler?
That's me.
Yeah. So what do you think, Eric? Can you see maybe a way we could simplify this? I'm basically, for the purpose of this expectation, I'm just telling you that a is given. So it's not random anymore for the purpose of this expectation. I'm telling you what it is. That's kind of what this thing is saying. So if this is given,
Right.
if that's known, then what about this? Is this also known?
Yes.
Yes. And the linearity property then says if I have something that's known in the expectation, if I have like a known quantity, here we saw it here. What happened to the D? It came out, right?
Yes.
Okay, so You see what's going to happen here?
You can take the F of A out.
Exactly. We can take out the FA because for the purpose of this expectation, it's deterministic. Now that does not mean that it's deterministic in an absolute sense because A here is still a random variable and f of A is therefore still a random variable. It's just when computing the expectation, that's when we treat it as if it was deterministic. Okay. You'll get a chance to practice on all this stuff on the next homework. Okay, any questions? Yes.
In the previous slide, it was a constant. It was a not random variable.
Right.
So we denoted constant and expectation of the remaining function. But here, f of a is a random variable. So
Right. So that's what I'm trying to say is that we have this particular property that says when you do a conditional expectation and you condition or you condition on A, or in other words, A is treated as if it's given, as if it's known, then for that purpose, this acts like deterministic. Right? So then it acts like the version on the previous slide. Okay. Any questions on this? Ready to move on to the next one? Okay. So what about the next one? If A and B are independent, what happens to that same? Let's see. I forgot my cheat sheet, and I'm trying to remember what I wanted to do here. So, oh yeah, let's see. Let me come back to that. I'll probably think about it. I'll remember it in a moment. Okay, let's do this other one. If we have, okay, so here we have a nested set of expectations. So we have expected value of FA given B. Now remember, this is random because it depends on the value of B, which is self-random. But then what's happening is this expectation is removing all that residual randomness. Once all that randomness to do with B is removed, it turns out you get back to expected value of FA without any conditioning. Okay, so that's, any questions on that? Yes.
So it's the random variable inside is like it depends on the B, so that it's given by B, right?
Well, so inside this expectation, you're asking the question, what is the average value of this if you know B? So that's what this is asking. What is FA if you know B? And then this is saying average overall possible B. And as a result, you're just going to look at the average value of FA with no consideration of B at all. Okay, so let me try to think. What was I doing with the independence?
I think you want to rewrite the first property without conditioning.
Well, I did that on the previous page. There's something, right, because we already did that one here. There's something I had in mind, and I'm not remembering it, but I might remember it.
Removing the conditioning.
Removing the,
Like expected value of G of B given A is equal to expected value of G of B.
oh yes, exactly, that's it. Thank you. So what I want to describe here is if I have something like, maybe I'll do this, expected value of FA given some random variable B, and B is completely unrelated to A, intuitively, it's like knowing B doesn't really tell me anything about A if it's independent, right? So it doesn't affect this average, doesn't affect this expectation. So as a result, we just have the expected value of FA. Okay, so this is when they're independent. Get this. And again, all of these properties can be proven with this basic definition and just a couple steps. It's a few lines. Okay. So let's see. So I've gone a little slower than I wanted. Are there any questions on this? Yes.
Where'd you get that equation? Because you said the expected value of the expected value is equal to E of A.
Are we talking about the second bullet or the third?
The second bullet.
Okay.
I don't know.
I mean, these are different ideas, so
Yeah.
I don't think you need to try to connect them. So in the first one, the key point is that if they're independent. So it only happens that way when they're independent. In the second case, they do not need to be independent. This always happens.
Yeah.
Okay. Okay, good. So any other questions? So that's really, those are the tools I wanted to review. And now we're ready to forge on and apply them to machine learning. And so we're going to build a statistical model, which is essentially the same one we were using in our demo, except, of course, our demo is done, we're generating actual numbers and so on, whereas here, we're going to be dealing with random variables. So here's our true model. The true model is basically, this is how the data really is generated. And this is regardless of whether it's our test data or our training data, it's always coming from this true model. So the true model has a noiseless part, which is purely a function. The targets equal a noiseless function of the features x plus some random noise, epsilon. That's going to be the model. We're going to use this model just for the analysis we're going to do. It's very simple, but it's what we want to do just to make the analysis possible. So in this case, the noise is definitely random. We're going to model it as a random variable. Notice I'm no longer going to be capitalizing, just going with our earlier notations, but we're going to think of it as random. And we're going to say that its mean is 0, meaning on average, it takes a value 0, and its variance is sigma squared. Okay. It might be Gaussian. It might be something else. But it's at this point, it's not important what the distribution is, except for the fact it has 0 mean and sigma squared variance. Okay. The feature vector x, we will also think of as random. And this mimics the fact that, when you think about the features that arise in a training set or that arise in some practical application, you never know what they're going to be until you see them, right? So in that sense, you can think of them as random. And you can think of them as coming from some underlying probability distribution, which you wish you knew. If you knew that, you could solve all these machine learning problems optimally, but that's the part you don't know. You just have a few examples of them for your training. Okay. So this model here, oh, and one other thing, this feature vector x is going to be independent of the noise statistically. So they're just completely separate stuff. There's this big set of feature data, and then the targets just have some random noise that's added to them. Maybe this is not a great model for every real-world application, but it's the one we're going to use. Okay, so we have this random epsilon, random x, and we're going to assume that this model applies both to our training and our test quantities. The training quantities, as always, are going to have i's on them, but sometimes in the same equation, we're going to have test quantities, and those will not have i's on them. So that's how we're going to distinguish training versus tests. And the independence that we see among all those random variables is all the xi's are going to be independent of themselves. All the epsilons are going to be independent of themselves. And all those 2n plus 1 random variables are all independent of each other. They're all just mutually independent. That's the assumptions we're going to make about the true model, like how the data is really manifesting. Are there any questions about that? Okay. So then we have a prediction model. This is something we create. It may be very far from the truth. Maybe it's our simple linear regression. Or maybe it's a polynomial. It's something that depends on the feature, and it depends on some parameter vector beta. But I'm plugging in the beta hat, which are the trained ones. So this is what I'm going to use, what I'm going to apply to my test data X. So somehow I get a bunch of training data, I collect that, I do some design, I get some beta hat vector, and now I'm ready to test it. And I'm saying that I plug in the true features here and I get out some approximation, some prediction of the truth, which is probably not going to be perfect. So there's a hat on this. There's a hat on this function because this is my prediction function. It might be totally different than the true function. And there's a hat on the beta vectors because just to represent that these are the trained ones. They're trained from some training data, some XY pairs. Remember, because the xi's are random, the yi's are also random, and therefore, when I plug those into my training procedure, my beta hats will also be treated as random. Okay, so that's part of the model. And the key thing to remember now is that the test features, the test error, and these training-derived betas, they're all mutually independent. So those are the things we're going to use when we do our analysis. The thing we're going to analyze is the mean squared error on our predictions y hat. And we're going to do this conditionally. We're going to say for a given x, this is our test x in most cases, what is the mean squared error on y? So by mean squared error, it's the expected value, the average value, of the squared difference between the true and predicted targets. Okay. We actually saw a deterministic version of this quantity earlier in the unit. Does anybody remember what that is? What's the deterministic version of this? Almost normalized RSS, right? Because, yeah. So RSS would grow with the training data or the test data, how many samples you have, right? Here, this is a per sample quantity. So that's where the normalization comes in. Because this is like a statistical, wait, sorry, I spelled that wrong. Statistical version of NRSS test. Sorry about my terrible handwriting. Okay. So this is going to be something that depends on the particular test vector that I use. And when you think about, like, what is this expectation averaging over? What kind of randomness is it removing? It's removing the randomness caused by the noise in the true target y, this one. And it's also removing the randomness due to the training data. It's sort of like saying, if you do an experiment where you keep getting different training sets and coming up with every new training set, you get a new beta hat. You just do this over and over and over and over again. What happens? What kind of a model do you get on average? How good is it on average? Okay, so that's where we're going. So we have a bit of a derivation to do. It looks bad. It's really not that bad. But I think it's just, after 5 p.m. on Friday, it's probably not the time to start this. So we'll save this. for Monday when we're ready to go. And then we'll immediately do a nice demonstration of this that I think will make it pretty intuitive. But that's where we are. So any last questions? Okay, great. Have a great weekend. See you guys on Monday.